Okay guys, here is one of the last videos for us on the divergence theorem. So last week you guys went through divergence and I did this little piece of the notes for us. This was actually in the last video from there. So let's move on then to the divergence theorem. The divergence theorem you're going to see is really helpful. So it says let S be a closed surface that encloses some region W in R3. So that is some three-dimensional region now. And suppose S is piecewise smooth. So what that means is at least there may be edges, but it's not completely messed up. It doesn't have asymptotes and shoot to infinity and have these really bad spots to it. And it's oriented by normal vectors pointing outward. So then let F be a vector field whose domain contains W. So it's defined on all of that region. Then, if you want this surface integral for that vector field, that is the same as a triple integral over the entire region of just the divergence of that vector field. And so here's the first example. I'm going to go through it, and then I'm going to switch over to that problem I told you that I would do for you. I wrote it up. I'll explain that, and then we'll come back and finish the notes. So this is to verify the divergence theorem for this vector field. It's f is y, comma x, comma z. And then over this region, x squared plus y squared plus z squared less than or equal to 4. Now x squared plus y squared plus z squared less than or equal to 4 is a sphere of radius 2 centered at the origin in three-dimensional space. And since it's less than or equal to, it's everything inside the sphere too. So it is a solid three-dimensional region in there. So to verify it, if I want to verify this, I need to check the left side, and this we already know how to do. This was previous homework that we've already done. That is just a surface integral over a vector field. This, though, is a triple integral. It involves the new thing, the divergence of the vector field, but at the end of the day, it's just a triple integral. So let's see how this works out. The left-hand side. Now, the left-hand side that I'm showing is I'm going to do the surface integral the way that we would normally do a surface integral. So, since we have a sphere, I'm going to use a spherical parameterization. That's the standard bounds for theta and phi. I know the normal vector. That normal vector I derived for you in another set of notes. And so for us, this is the normal vector. Once I feed my parameterization into this vector field right here, I get this. And when I dot this with that n vector, it works out to be this right here. If I then integrate, and phi goes from 0 to pi, and theta goes from 0 to 2 pi, I put this in, I get 32 pi over 3. But to do this, you have a sine cubed and a sine, and the sine cubed is for phi, and then you got a sine theta, cosine theta. So it takes some reduction formulas, it takes some trig tricks, it takes some, sine of 2 thetas, 2 sine theta, cosine theta, and some of those formulas to get through it. But still, you would have to come up with a parameterization, compute the normal vector, dot or feed that parameterization into the vector field, then take a dot product of that newly fed parameterization into the vector field and dot that with the normal vector. To find the normal vector, you technically need to find the tangent vector in the theta direction and the tangent vector in the phi direction. Take the cross product of those two vectors to get that vector pointing out, and you want to make sure the sign's right so that it truly is an outward pointing normal. But if you do all that, it comes down to 32 pi over 3. Now, the left-hand side. The left-hand side is to just do a triple integral over that region for the divergence of it. And so, if I do that, the divergence of f is the x derivative of y, which is 0, the y derivative of x, which is 0, and the z derivative of z, which is 1. So the divergence of that vector field is just 1. And if I feed the the coordinates in, I could feed all the coordinates in with a rho and a theta and a phi and all of that. But since this is 1, when you integrate 1 in a triple integral over a three-dimensional region, it becomes the volume of that region. And since that region was a sphere of radius 2, you know the volume of a sphere is 4/3 pi r cubed. The radius was 2, so 2 cubed is 8. 8 times 4 is 32, so it's 32 pi over 3, and that's exactly what we got the first time. Notice how much easier that is than having to parameterize, find a normal vector, feed it into the vector field, take a dot product, and then still perform this double integral. Okay, if you look at my next example, this says use the divergence theorem to compute that surface integral over a rectangular prism, a box, basically. And so in order to do that, I'm going to switch over here. So a number of you in office hours came at different times and asked if I could do 15. And this is from the surface integral from vector field homework. So here is that homework. And we're looking at problem 15 right there. I've copied it and pulled it out. Since x goes 0 to 1, y goes 0 to 1, and z goes 0 to 1, we just have this unit cube in that first octant. That cube now is not just one continuous surface. It's actually 6 surfaces. It's the bottom side, the top side, the left side, the right side, the front side, the back side. And so, to do a surface integral straightforward, I have to parameterize all 6 surfaces. So this actually, one problem turns into 6 problems. And we're going to go through it. So here it is. The bottom face, that's the floor of this box. What I do know about the floor is that z is 0 on the floor. So my parameterization then would be let x be whatever, let y be whatever, but z has to be 0. And then to limit it, I know x goes 0 to 1 and y goes 0 to 1. Once I have that parameterization, take the x derivative, it's 1, 0, 0. Take the y derivative, 0, 1, 0. If I dot them, I get 0, 0, 1. But look, that points up, so I put this note right here. 0, 0, 1 is, it just points straight up 1 unit in the z direction. So that's this right here. Well, that's pointing into the box. I need an outward pointing normal. So I take this and I change it right there. So I manipulated that to make it be an outward pointing normal. That was stated in that problem. Then I feed my parameterization into the vector field. Well, the vector field is always 2 zeros first, and then whatever the y and the z are. So then this is y plus 0. It'll just be e to the y. Then when I dot these two, I get 0 times 0 plus 0 times 0 plus negative 1 times e to the y. That will be negative e to the y. Now when I'm done, I'm going to integrate this function with those limits right there. But we're going to put that on pause for a second. So that's just the bottom face. Now we take to the top face. On the top face, what I do know is z equals 1 there. So I'm going to let x be whatever, y be whatever, but this time z has to be 1. I put my bounds for x. X goes from 0 to 1, y goes from 0 to 1, and find g sub x, 1, 0, 0, gy, 0, 1, 0. That's exactly this over here, so I know the normal vector, and that points up, and because up is outward for the top, then I don't need to manipulate that normal vector. So now I'm going to dot this. Oh, then I need to feed this parameterization into the vector field. So I just add those two, y plus 1, and that's in the third slot. Then I get 0 times 0, 0 times 0, and 1 times e to the y plus 1. So when I'm done, I'm going to integrate e to the y plus 1 with those limits right there. Okay, now for the right face. That face, y is 1. So I put y as 1. Now my g is, instead of an xy function, it's going to be a function of x and z. Then, since I know y is 1, it'll just be x1z. And we take g sub x, that's going to be 1, 0, 0. G sub z is 0, 0, 1. I dot those two, and I got 0, 1, 0. And 0, 1, 0 is just 1 unit in the y direction, so that does point out of the box. And so that is good. That is an outward pointing normal. I feed g into the vector field. It just adds those two and puts it as a power of e in the third slot, and so there's the e to the 1 plus z right there. When I dot this, I get 0 times 0 is 0, 0 times 1 is 0, and e to the 1 plus z times 0 is 0. When you add them up, it's 0. So the right face doesn't do anything for us. Okay, left face. The left face, y is 0. So we have x, 0, z. Take the derivatives, find the normal vector. It did come out to be 0, 1, 0, and it's because this was exactly the same as that, and so I stole that normal right there, but it wasn't outward because it would point that direction. I need it to point outside the box, so I had to add that negative in there. Feed the parameterization into f, so we add those two and put it as a power of z. 0 times 0 is 0, negative 1 times 0 is 0, and 0 times e to the z is 0. So that f of g dot n is 0, so the left face will not contribute anything to that integral. Now the front face. The front face, x is 1 on there, so I've got 1yz. Y derivative, z derivative, compute it, feed it in, you add those two and put it as a power of z. 1 times 0 is 0, 0 times 0 is 0, 0 times e to the y plus z is 0. The front face doesn't add anything either. The back face, x is 0 in that case. So we have x is 0. So I have 0, y, z. It's going to be the same tangent vector here, except it's going to point into the box. Now it'll point this way, and I need it to point outside. And so I manipulated that from this right here. Then when I dot, I get 0 plus 0 plus 0. That's going to be 0 also. So that doesn't contribute anything. So you guys, I did 4 faces, parameterized them, fed them into a cross product, with the tangent vectors to find a normal vector. Then I fed the parameterization into a vector field. Then I took the dot product of that with that normal vector, and it came out 0. And if you integrate 0 over any interval, the answer is still 0. So it looks like the only 2 faces that are going to contribute to this is the top and the bottom face. But that should make sense because e to anything is always positive. You know the graph. And so this is always vectors pointing in the upward direction. And so all of these are parallel to where the vector field's going. So it's just running right through them. But the bottom, it will have vectors pushing through the bottom, and the top, it will also. And so it should make sense that the bottom and the top will be the only things that contribute as an afterthought. You wouldn't have seen that at first. So then over here, we said, okay, well, if we want that, that surface integral, it should be the surface integral over the bottom plus the top plus the left plus the right plus the front plus the back. But those are all 0. So I know e to the negative y, 0 to 1 on y, 0 to 1 on x, and e to the y plus 1, 0 to 1 on y, 0 to 1 on x. If you work this out, it does come out to be e minus 1 quantity squared. Okay, that's a lot of work. That is 6 parameterizations, 6 normal vectors, 6 dot products, and 6 double integrals. However, if at this time, and we didn't have it at the time, if we had the divergence theorem, the divergence of this is the x derivative of that 0 plus the y derivative of that 0 plus the z derivative of that is e to the y plus z. So the divergence is just e to the y plus z. So there's divergence right there. And I know z is 0 to 1, y is 0 to 1, and x is 0 to 1. And if you do that triple integral one time, you get the exact same answer we got the other time. You guys, this is eons faster than the old way, what I call the old way. And so it is in our interest to use that to our advantage if we can. So back to this then. Notice this is just a cube. It is some sort of a rectangular box. And because of that, if we did it the old way, we would need to do all 6 surfaces and do f of g of xy dot n, blah, 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 do that whole thing. Or we could just do, figure out the divergence. So it should be 2x plus 0 plus e to the z. So there's the divergence right there. And then I know x goes 0 to 2, y goes 0 to 3, and z goes 0 to 1. And there you have the answer. But if you did it the other way, you would have to do it exactly how I did this over here and do all 6 of the faces and then do double integrals for each one of those. So it does help us there. And this, we didn't do it both ways. We just did it using divergence straight up. This one, we have this boundary of this plane right here in the first octant. And so in order to do this, we have this plane, and it does make a solid. So you can see it's sort of that pyramid in there. So this goes down, this is down, and then this is out. But then the front side is shaded that way. So it is solid. And to do that, we need to compute the divergence. So the x derivative is 2x, the y derivative is nothing, and the z derivative is nothing. So divergence is just 2x. Well, if I'm going to do that, then we have dz, dy, dx. And so z goes from 0 to the plane. Well, if that's the plane, I can solve it and say then z should be 12 minus x minus 2y all over 4. And that works out to be that right there. And then I know in the xy plane, then on the floor, it looks like this. I can figure out the equation of the line. So I dropped 6 and ran 12. So that's a slope of negative 6/12, or negative 1/2. The y-intercept is 6, and so there's the equation of the line. So then y is going to run from 0 to that line. So there's 0 to that line right there. And once you have that, x gets the whole gamut, and it goes 0 to 12. And if you ran that whole thing, it comes out to be 216. If we did it the other way, you would have to do 4 surface integrals, because you would have one for this face triangle, you'd have one for that face triangle, one for the floor triangle, and one for the slanted triangle that actually kind of creates the roof of that lean-to, or whatever you would call it. So that's the last page that I have there, and that completes the divergence material that you need to know. Again, those problems, they're pretty straightforward, and most of them, if they're in there, it's probably a nightmare if you were going to do them the old way, especially if it's built up of pieces like rectangular squares or rectangles, because wherever those come together as an edge, you have to break your parameterization right there. And so, but on a sphere, it's completely curved and there is no boundary to it, and so we don't run into that same problem on a sphere. But the edges on a cube are where we can't take a derivative, and because there's tons of different tangent lines, and for that reason, you can't really find a normal vector on those edges, and so then you have to break it apart and do that. So I hope that helps you. That's the last one for this week, and I did do the number 15 from the homework and showed it to you both ways, the old way and the new way, using the divergence theorem. Okay? Take care, guys. I'll talk to you soon, and just hang in there.